Swayam Prabha. Digital India. Educated India.
Okay, now we are going to discuss the another technique, the last technique. I call it as a Kuntakar technique. And before going to discuss the Kuntakar technique, we have to revisit the optimization of linear programming and nonlinear programming problem. Therefore, let us start some introduction related to optimality ideas. So, to approximate the difficulty in the approach, let us distinguish between the factors that make a LPP, linear programming problem, and NLPP is a nonlinear programming problem as more complex. So, the algorithm for solving LPP is based on the property that optimal solution ought to be found at the extreme points of the convex polyhedron. So, optimal solution mean the solution are feasible or infeasible, bounded or unbounded, and no solution also sometimes may come. And exactly the meaning is optimal is maximum of minimum equal to minimum of maximum, and these points we have to identify with the help of the convex polyhedron. So, this implies that we limit our search to corner points, and this could be completed in a finite number of iterations. But nonlinear programming problem, the optimal solution can be anywhere along the boundaries of the feasible solution or anywhere within the feasible region. Therefore, sometimes it may be the bounded solution or unbounded solution for NLP. So, linear relationship between the decision variable is very easily amendable to linear algebraic transformation, but nonlinear relationship should be dealt with extreme care, resulting in complex situations. So, the nonlinear nature of the relationship results in distinction between the local solution and a global solution. This means that any solution that is locally optimal has to be tested for its optimality over the entire feasible region, and not only at the extreme point as has been possible in an LPP, and also means that we have to apply simplex algorithm and do not suffice to solve NLPPs. So, the structure of the optimal problem is first you have to formulation of the problem and identify the variable and constraint, and establish the relationship between the variables and constraint by the constructing the model and identifying the possible alternative solution, call it as a basic feasible solution, and give an optimality test to basic feasible solution and select the optimal solution and install the test and establish the solution with the model and establish the controls, implement and maintain the solution. So, this is the flow chart. This is a hierarchical way to choose the solving the operation of the research problem, that is op search mean management technique we have to do like this. So, operation research problem we have to do this type of the hierarchical way to maintain the problem. Now, some of the points to be remembered while building a model, they are: number 1, when we can solve the situation with a simple model, do not try to build a complicated model. Build a model that can be easily fit in the techniques available. Do not try to search for a technique which suit your model. So, in order to avoid a complication while solving the problem, the fabrication stage of modeling must be conducted rigorously, and before implementing the model it should be validated or tested properly. Use the model for which it is deducted, and do not use the model for the purpose for which it is not meant. without having a clear idea for which the model is built to not use it. It is better before using the model you consult an operation research analyst and take his guidance, and models cannot replace decision makers. It can guide them, but it cannot make the decision, and do not under the impression that the model solves every type of the problem. So, the model should be accurate as possible, the model should be as simple as possible, and benefit of the model are always associated with process which it is developed. Next, we have advantage. A model provides a logical and systematic approach to the problem, and it provides the analyst a base for understanding the problem and think of the method of solving. The model will avoid the duplication work in solving the problem. A model fixes the limitation and scope of an activity. Model helps the analyst to find a newer ways of solving the problem. Model saves resources like money, time, etc. Model helps analysts to make complexity of a real environmental simple. And another point is the risk of tampering of a real object is reduced. When the model of the real system is subject to the experiment analysis, and model provides a distilled economic description and explanation of the operation of the system they represent. So, the characteristic of good model. So, the number of parameters considered in a model should be less to understand the problem easily, and the good model should be flexible to accommodate and necessary information during the stages of the building the model. A model must take less time to construct. A model may be accompanied by a lower and upper bounds of the parameter values. Next, steps in constructing a model. A problem environment analysis and formulation. One has to study the system in all aspects. If necessary, make relevant assumption, have the decision for which he is constructing the model in mind and formulate the model. And model construction and assumption, identify the main variables and constraint and relate them logically to arrive at the model. Testing the model after the formulation before using check the model for its validity. Now, let us go to small numerical example to try to understand the difference between the LPP and NLPP. Example, if you take z equal to x1 minus 8 the whole square plus x2 minus 4 the whole square whole power half, subject to the constraint x1 plus x2 less than or equal to 8 minus 3x1 plus 2x2 less than or equal to 6. Now, here both x1 and x2 are positive. So, this problem can solve graphically, and we find the feasible point lies at the shortest distance away from the point 8, 4. So, the optimal solution is x1 6, x2 equal to 2 will come, where the indifferent circle z equal to 2.828 is a tangent to the boundary of the feasible region. So, the optimum solution does not lie in the extremum point, and thus simplex type of the algorithm could not solve the problem. Therefore, the feasible existence of local optima might not give an optimal solution for the same region. Therefore, it may also possible to solve NLPP, that the feasible region nonlinear programming problem, that the feasible region may consist of two or more entirely disconnected sets of points. So, this is the expression corresponding to the graph. After solving this one, see one is lies here, another is lies here, and it will be what not pakka answer to the question, and somewhat it is more or less a nonlinear type of the programming problem, where z having a 2.5 one of the curves, and another curve is 2.828, and we could not predict accurately, whereas approximately we can predict. So, that is why it goes to the NLPP. Now, how to mathematically formulate the problem? One real time example, a company manufactures of two products x and y, which requires the following resources. The resources are the capacities machine M1, M2, M3. So, the available capacities are 50, 25 and 15 hours respectively in the planning period. Product X requires 1 hour of machine M2, 1 hour of machine M2 and 1 hour of machine M3, and product Y requires 2 hours of machine M1 and 2 hours of machine M2 and 1 hours of M3, and the profit contribution of the product XY are 5 and 4 respectively. So, the contents of the statement of the problem can be summarized as follows. So, machines and products availability in hours. So, M1, M2, M3 corresponding for X is 0, M1 corresponding Y is 1 and M2 corresponding X is 1 is given, and M2 corresponding Y is 2 is given, M3 corresponding X is 1 is given, M3 corresponding Y is 2 is given, the 1 is given. Therefore, according to the table we can design like this, and maximum availability of M1 is 50 and for M2 is 25, M3 is 15 given here. So, this is the value you have to use the availability hours, and corresponding profit of this and this is given 4 and 5 and 4 corresponding XY. Therefore, we form a table like this. So, the above example is a XY or competing the candidate on the variables. So, the machine capacities are available. Therefore, the profit contribution of the X and Y are given. So, let us formulate the model. So, let the company manufacture X units X and Y units of Y, so that the profit contribution of X and Y are 5 and 4 respectively. Therefore, the objective problem is to maximize the profit Z equal to 5x plus 4y, and it should be done. So, the utilization of the machine hours by product X and Y should not be exceed the availability of the capacity. Now, according to the table for machine M1, right, machine M1, machine M2, machine M3 is 0x plus 2y less than or equal to 0x plus 2y less than or equal to 50. We understand. So, this is the first equation, and this is the second equation, and third equation we have corresponding to this. I hope all of you understand. The different colors are used so that the x plus 2i less than or equal to 50 and 1x plus 2i less than or equal to 25 and 1x plus 1y less than or equal to 25 comes from the table. So, this is the linear structural constraint, but the company cannot stop the production X and Y or the manufacture any amount of X and Y, and it cannot be manufacture negative quantities. Therefore, both X and Y are positive. Therefore, it is non-negativity constraint. As the problem has got objective function, structural constraint and non-negative constraint, therefore, there exists a linear relationship between the variables constraint in the form of inequalities. Therefore, the problem satisfies the LPP. Now, we go to the next problem. A retail store stocks two types of shirts A and B. They are packed in attractive cardboard boxes. During a week, the store can sell a maximum of 400 shirts of type A and a maximum of 300 shirts of type B. The storage capacity, however, is limited to a maximum of 600 of both type combined. So, type A shirt fetches a profit of rupees 2 per unit, and type E a profit of rupees 5 per unit. How many of each type of the store should stock per week to maximize the total profit? Formulate the mathematical model of the problem. Here, shirts A and B are a problem variable, that the store stock A unit of A and B units of B, as the profit contribution A and B are 2 and 5 respectively. So, the objective function is Z equal to 2A plus 5B subject to the constraint. according to the given problem, and structural constraints are stores can sell 400 units of shirt A and 300 units of shirt B, and the storage capacity of put together we have 600 units. Hence, the structural constraints are 1 into A plus 0B greater than or equal to 400. Another one is A plus 1B less than or equal to 300. So, for sale capacity is 1A plus 1B less than or equal to 600. For non-negative constraint for both A and B is positive. Hence, the model is Z equal to 2A plus 5B such that 1A plus 0B less than or equal to 400 and 0A plus 1B less than or equal to 300, and A plus B is less than or equal to 600 from the above analysis. Therefore, both A and B are positive. I hope all of you can understand how we can make the literally given how to make the equations of the objective function subject to the constraint, and the question is maximize the total profit, therefore maximize you put it. Then we have objective with the help of the statement you get it. Next mathematical problem, modeling. A ship has 3 cargo holds, forward, aft and center. The capacity limits of forward is 2000 tons and 1 lakh cubic meters, and center has 300 tons and 1,35,000 cubic meters, and aft has 1500 tons and 30,000 cubic meters. So, the following cargoes are offered. The ship owners may accept all or any part of their each community. So, commodity, amount in tons, volume per ton in cubic meters, profit per ton in rupees. So, commodity having A, B, C. So, the amount in tons is what? Corresponding is 600, 4000 and 200 given. Volume 60, 50, 25 is given, profit is given. Now, we have to make a equation. So, here to preserve the trim of ship, the weight in each hold must be proportional to the capacity in tons. How should the cargo be distributed so as to maximize the profit? Formulate this as a linear programming problem. So, the problem variable are commodities A, B and C. Let the shipping company ship A unit of A, B unit of B and C unit of C. Therefore, the objective function is Z equal to 60A plus 80B plus 50C such that subject to the constraint we have 6000A plus 4000B plus 2000C less than or equal to 6500, because the 6500 is a summation of 2, 3, 15, 100, 20, 2000, 3000 plus 1500. The tons of commodity is 6000 and each ton occupies 60 cubic meters. So, there are 100 cubic meters capacity is available. Similarly, the availability of commodity B and C having 80 cubic meter, and the capacity inequality will be 100A plus 80B plus 80C is less than or equal to 2,65,000 because of 1,135,000 and 30,000 is given. 1 lakh plus 1 lakh 35,000 plus 30,000 is given. Therefore, the LPP model is maximize Z equal to 60A plus 80B plus 50C such that 6000 A plus 4000B plus 2000C less than or equal to 6500, and 100A plus 80B plus 80C is less than or equal to 2,65,000, and here 8B equal to 4000 by 50 equal to 80, 8C equal to 2000 by 25 equal to 80. Therefore, corresponding we have 100A plus 80B plus 80C is 2,65,000 for all A, B, C are positive. Similarly, so far we discussed maximize. Now, we go to the minimize the model. So, a patient consult a doctor to check is ill health, doctor examines him and advises him that he is having a deficiency of 2 vitamins, let it be A and B, A and D, vitamin A and vitamin D, and doctor advises him to consume vitamin A and D regularly for a period of time, so that he can regain his health. Doctor prescribes a tonic X and tonic Y, which are having vitamin A and D in certain proportion. Also advises the patient to consume at least 40 units of vitamin A and 50 units of vitamin D daily. So, the cost of the tonics X and Y, or the proportion of the vitamin A and D that present in X and Y, are given in the table below. So, form the LPP to minimize the cost term. So, vitamins corresponding tonics daily requirement in units are respectively A and D are vitamins. The tonics are corresponding X corresponding to A is 2, Y corresponding to A is 4, and similarly for D equal to 3 and Y equal to 2. So, maximum daily requirement is 40 and 50 respectively A and D. Therefore, the cost of the each tonics is 5 and 3 rupees per unit. So, this is the data given. Now, making use of this data, we have to bring a mathematical problem, that is called it as mathematical modeling. So, let patient purchase X units of capital X and Y, capital X and Y for capital Y. So, the objective function is Z equal to 5x plus 3y based on the cost. So, they asked the minimize, therefore, minimize the cost, therefore, minimum Z equal to 5x plus 3y will come. Now, for A vitamin, we have a 2x plus 4y is the first equation, and which is maximum of daily requirement unit is 40. Therefore, here at least word indicates the patient can consume more than 40 units, but not less than 40 units of vitamin A daily. Similarly, the inequality for the vitamin D is 3x plus 2y greater than or equal to 50. So, for non-negativity constraint, the patient cannot consume negative units, hence both x and y must be positive. Therefore, the LPP model for the problem is minimize Z equal to 5x plus 3y subject to the constraint, 2x plus 4y greater than or equal to 40 and 3x plus 2y greater than or equal to 50, and both x and y are positive. So, next problem, a machine tool company conducts a job training program at a ratio of 1 for every 10 trainees. The training program lasts for 1 month. From past experience, it has been found that out of 10 trainees hired, only 7 complete the program successfully. So, the unsuccessful trainees are released. So, the trained mechanists are also needed for matching. So, the company's requirement for the next 3 months is as follows. January 100 machinist, February 150 and March 200. In addition, the company requires 250 trained machinists by April. So, there are 130 trained machinists available at the beginning of the year. So, payroll cost per month is each trainee is 400 per month, each trained machinist is 700 per month, and each trained machinist who is idle is 500 per month. So, the labor union forbids ousting trained machinist, built a LPP for produce the minimum cost hiring and training schedule and meet the company's requirement. So, the solution is there are 3 options for trained machines as per the data. Number 1, a trained machinist can work on machine. Number 2, he can teach. Number 3, he can remain idle. So, it is given that the number of trained machinists available for machine is fixing. Hence, the unknown decision variables are number of machinists goes for teaching and those who remain idle for each month. So, let A be the trained machinist teaching in the month of January, B be the trained machinist idle in the month of January, C be the trained machinist for teaching in the month of February, D be the trained machinist remain idle in February, EB trained missions for teaching in March. FB the trained mission remain idle in the month of March. So, the constraint can be formulated by rule that the number of machinists used for machining teaching idle. So, the number of trained machinists available at the beginning of the month for January is 100 plus 1A plus 1B greater than or equal to 130. For February, 150 plus 1C plus 1D equal to 130 plus 7A. Here 7A indicates that number of machinists trained is 10 into A equal to 100A, but only 7 of them successfully complete the training is 7A. For the month of March, 200 plus 1E plus 1F is greater than or equal to 130 plus 7A plus 7C. So, the requirement of trained machinists in the month of April is 250. The constraint for this will be 130 plus 7A plus 7C plus 7E greater than or equal to 250. Therefore, the objective function is minimize Z equal to 400 into 10A plus 10C plus 10E plus 700 into 1A plus 1C plus 1D plus 400 into 1B plus 1D plus 1F, and non-negative constraint is A, B, C, D, E, F all are positive. Therefore, minimize Z equal to 400 into 10A plus 10C plus 10E plus 700 into 1A plus 1C plus 1E plus 400 into 1B plus 1D plus 1F such that what 100 plus 1A plus 1B greater than or equal to 130 and 150 plus 1C plus 1D greater than or equal to 130 plus 7A, because the maximum of 130 associated with 7 of them successfully completed, therefore, add with 130 to 7A. For third case, 130 plus 7A plus 7C because of month March, and fourth one is month of March and associate with April. Therefore, 130 plus 7A plus 7C plus 7E greater than or equal to 250. So, the subject to the constraint will be the 4 equations, and A, B, C, D, E, F all are positive. Next, we have another example. A company manufactures 2 products A and B on 2 machines. Whatever is manufactured is sold in the market. As the market for the product is good, so the capacity of machines are limited to produce daily 180 units of the product A and 60 units of product B. So, the raw material supply required for the product is limited to produce 600 units per day. So, the labor required is 160 man days and the organization has 160 men on the roll. So, the production of A requires 1 man day hour of labor and that of product B is 2 man day of hour. So, the company objective is to maximize the total profit if the sales price relationships are given below. So, the product, unit price required, quantity demand is given, cost function is given, 2 products A and B and corresponding unit price is P1, P2 and quantity demand is 1500 minus 5 P1 for A, 3800 minus 100 P2 for B and cost function is 200 A plus A square, 300 B plus B square, 0.1 B square. For A, 200 plus A plus 0.1 A square. For B, 300 B plus 0.1 B square. So, the above table A and B are the numbers of units A and B. So, this can be written as 1500 minus 5 P1 plus B equal to 3800 minus 10 P2. So, the solution is R be the revenue on the sales, C be the cost of the production. So, the profit equal to revenue minus cost, which is equal to R equal to P1A plus P2B, and P1 is 300 minus 0.2A into A and P2 is 380 minus 0.1 into B. So, that 300A minus 0.2 A square plus 380B minus 0.1 B square plus C is 200A plus 0.1 A square and then 300B plus 0.1 B square. Therefore, maximize Z equal to R minus C and which is equal to 100a plus 0.3 a square plus 80b plus 0.2 b square, and we have to check P1, P2, and we have to compute the problem. So, let us construct A is less than or equal to 80 and B is less than 60 and 5A plus 6B less than or equal to 600 and A plus 2B less than or equal to 160, and both A and B are positive. Therefore, the problem is NLPP. So, this shown in the figure 14.2, where we have to check the problem is global minimum or global maximum, or where the infection is coming, where the global minimum coming, where the global maximum coming. So, these are all the things we have to check with the help of the objective function to the subject to the constraint, and we have to check for non-linear optimization to determine the global minimum, and we have to use with computational aspects to lead the local minimum, and we have the procedure to determine local minimum really the global minimum, and this simplex procedure we have to check it out, and the reason why we have some mathematical concept to deal with LPP. So, we know what is the meaning of global minimum. So, function is a global minimum at the point x naught of a set, then f of x naught is less than or equal to f of x for all x in k. For the local minimum, we have the point x naught of the set of the point, if and only if there exists a positive integer f of x naught less than or equal to f of x. So, in which norm of x minus x is subset of epsilon. So, in this case, for a single variable, the necessary condition for particular solution x equal to x star to be either maximum or minimum. So, x star is a local minimum, then it is strictly convex with the neighborhood, and second derivative of x star is positive, then is 0. We have to move the higher derivatives of global minimum and global maximum and identify one of them yields the smallest or the value of the y of x. Now, we have a Lagrange's multiplier is most important for this topic. Here the optimization problem continuous function is discussed. Nonlinear programming problem is also composed with some differentiable objective function, and equality side constraint the optimization may be achieved by use of Lagrange's multipliers. So, the Lagrange's multiplier measures the sensitivity of the optimal value of the objective function and subject to the constraint bi in the problem. So, z of f of x1, x2, xn is a subject to the m constraint. So, let us formulate the Lagrange's function. L is defined as L of x1, x2, xn, lambda 1 and so on minus summation lambda I of gi of x1, x2 and so on xn equal to bi, where I varies from 1 to m, and lambda 1 to lambda n are called Lagrange's multipliers. So, the optimal solution of the Lagrange's function is determined by taking the partial derivative of L with respect to each variable. So, the Lagrange's multiplier setting the each partial derivative to 0 and finding the values to make the partial derivative 0. Therefore, the solution will be the solution of the original problem. Now, let us go with one problem. Find the extreme value of z equal to f of x1 x2 equal to 2 x1 x2 subject to the constraint x1 square plus x2 square equal to 1. Now, the technique is L of x1 x2 lambda you have to do, that is L of x1 x2 is 2 x1 x2 then plus lambda times of 1 minus subject to the constraint of x1 minus x1 square plus x2 square. Now, it is partially with respect to x1 equal to 0 then, so that it will be what here 2 x2 will come, here partially with respect to x1 is minus 2 x1 x2 lambda, and second one is 2 partially with respect to x2. So, here is 2 x1 will come, it should be minus, so minus 2 x2 lambda will come, and then 0 equal to dou L by dou lambda which is equal to 1 minus x1 square minus x2 square, because with respect to lambda it becomes 0 first term. Second term is dou L by dou lambda is 1 into 1 minus x1 square minus x2 square. Now solve these three equation, solve these three equation, we have x2 and x1 will come in terms of x1 lambda, x1 is x2 lambda, therefore x1 equal to x1 lambda equal to x2 lambda square. So from this either x2 equal to 0 or lambda equal to plus or minus 1. If x2 equal to 0, then x1 equal to 0. Therefore the constraint x1 square plus x2 square equal to 1 is not satisfied. Therefore x2 is not equal to 0, either lambda equal to 1 or lambda equal to minus 1 is the inference of the values. So we have a cases, case 1, if lambda equal to 1 and x1 equal to x2, then 2x1 square equal to 1 implies x1 equal to plus or minus root 2 by 2. If lambda equal to minus 1, x2 equal to minus x1, therefore x1 equal to plus or minus root 2 by 2. Therefore we have solutions plus or minus, we have two types, and case 2 x2 x1 have a plus or minus root 2 by 2. Therefore root 2 by 2 and x2 is minus root 2 by 2, minus root 2 by 2 minus root 2 by 2 and then 1 for corresponding lambda. And other cases root 2 by 2 minus root 2 by 2 minus 1. Next one is root 2 by 2 comma root 2 by 2 comma minus 1. These are all the solution to corresponding x1 x2 lambda, and here k equal to x by x1 square plus x2 square equal to 1 is closed and bounded. Therefore f of x equal to 2x1 x2 is continuous. So f is both maxima and minima over k. Therefore the maximum of f over k is 1, occurs at both root 2 by 2 comma root 2 by 2 and minus root 2 by 2 comma minus root 2 by 2. Therefore the minimum value of f is minus 1, occurs both minus root 2 by 2 comma root 2 by 2 and root 2 by 2 comma minus root 2 by 2. So now we have a Kuntakar condition. So if the constraints of a nonlinear programming problem of inequality form, we can solve by using the Lagrange's multipliers, which are slightly modified. Let us consider the maximize the problem z equal to x1 x2 and so on xn subject to the constraint g of x1 x2 xn less than or equal to c, where all x1 is positive. So this constraint can be modified if h of x1 x2 is negative by introducing h of x1 is equal to g of x1 is equal to c. Therefore maximize z equal to f of x subject to the constraint h of x is less than equal to 0 and x is greater than or equal to 0. So the problem can be slightly modified by introducing a new variable s and defining s dash equal to minus h of x or h of x, which is equal to s square equal to 0. H can be interpreted as slack variable. It appears its square in the constraint equation so as to ensure the being non-negative. So the problem can be restated as optimized z equal to f of x subject to the constraint h of x plus s square equal to 0, and the problem constraint optimized in n plus 1 variable with a single equation constraint can be solved by Lagrange's multiplier method. Now to determine stationary point, then the Lagrange's function L of x comma s comma lambda is f of x minus lambda into h of x plus s square. If lambda is a Lagrange's multiplier, then necessary condition for stationary points are dou L by dou xj equal to dou f by dou xj minus lambda into dou h by dou xj equal to 0 for j equal to 1 to n, dou L by dou lambda equal to minus h of x plus s square equal to 0, and dou L by dou s equal to partially with respect to s of L is minus 2s lambda equal to 0. So we have a equation 1, 2, 3, and equation 3 gives if equal to 0 which is receives the lambda equal to 0 and s equal to 0, and equation 2 implies h of x equal to 0 and 2 and 3 together implied lambda into h of x equal to 0 of s equal to 0. Therefore, the slack variable was introduced to convert the unequal constraint to an equal one. So, it may be discarded as S square is positive and 2 gives h of x is less than or equal to 0, and h of x whenever h of x 0 from equation 4 we get lambda equal to 0, whenever lambda is positive h of x equal to 0 and lambda is unrestricted then h of x is negative. So, the problem reduces the equation constraint of necessary condition of the point is fj minus lambda into hj equal to 0, lambda h equal to 0, maximize f is h less than 0 subject to the constraint lambda greater than equal to 0 and h is less than equal to 0. General case, the constraint optimization of nonlinear function n variable under m less than n inequality constraint, and consider nonlinear programming problem maximize z equal to f of x subject to the constraint g of x is less than or equal to ci, and introduce hi of x equal to gi of x minus ci, and the inequality constraint can be written as h dash of x is less than 0 for I equal to 1 to m. Now, introducing the slack variable 1 to m and hi of x plus si of 0 equal to 0. Therefore, the inequality constraints are converted to equality ones, and the stationary value of x can thus be obtained the Lagrange's multiplier method, and Lagrange's function is L of x comma s comma lambda equal to f of x minus summation lambda into hi of x plus si of c, where lambda equal to lambda 1 and so on lambda m Lagrange's multiplier. So, the necessary condition of f of x to be maximum are dou L by dou x j equal to dou f by dou x j minus summation j equal to 1 to m lambda I dou hi by dou x j for j equal to 1 to n, and dou L by dou lambda I equal to hi plus si is equal to 0 square for all I equal to 1 to m, dou L by dou si equal to minus 2 si lambda I equal to 0 for I equal to 1 to m. Therefore, L stands for L of x comma lambda into f of x into hi. Use the same argument as a single inequality case. In the previous case, equation 3 either lambda equal to 0 or si equal to 0. Here, the condition 3 and 2 together are the condition of 5, 6, 7. Therefore, for 5 lambda into hi equal to 0, I varies from 1 to m. For 6 hi is negative and I varies from 1 to m. For 7 lambda is positive and corresponding I equal to 1 to m. And we have a Kuntakar condition for maximum or restricted to fi equal to summation I equal to 1 to m lambda j hj I, and lambda hi is negative, I varies from 1 to m, and lambda is positive, I varies from 1 to m. Therefore, h for ij equal to dou hi by dou xj maximize subject to the constraint of hi is negative. Now, sufficient condition for Kuntakar is Kuntakar condition must be global maximum point, and h of x plus s square is 0, then necessary condition for lambda s square is 0, and h of x is convex and lambda is positive, then lambda into h of x is also convex. If negative h of x lambda is concave, so we conclude that f of x minus lambda hx, and hence f of x minus lambda into h of x plus s square equal to L of x comma s comma lambda is concave in x. So, we have a problem, maximize z equal to 3.6 x1 minus 0.4 x1 square plus 1.62 x2 minus 0.2 x2 square subject to the constraint 2 x1 plus x2 less than or equal to 10, and both x1 x2 are positive. Here f of x equal to 3.6 x1 minus 0.4 x1 square plus 1.6 x2 minus 0.2 x2 square. Therefore, g of x into 2 x1 plus x2 comma c is 10, and h of x equal to g of x minus c equal to 2 x1 plus x2 minus 10. So, according to Kuntakar condition, dou x by dou x1 minus lambda into dou hx by dou x1 equal to 0, and dou f of x by dou x2 minus lambda into dou hx dou x2 equal to 0. Therefore, lambda into hx equal to 0 implies hx equal to 0. This implies lambda is positive, and the Lagrange's multiplier lambda can be calculated with the simplification of the above equation is 3.6 minus 0.8 x1 equal to 2 lambda, and further divide through on both sides we have 1.6 minus 0.4 x2 into lambda. Therefore, lambda times of 2 x1 plus x2 minus 10 equal to 0, subject to the previous this third equation. We have lambda is 0 or 2 x1 plus x2 minus 10 equal to 0, but lambda is positive. Therefore, 2 x1 plus x2 minus 10 is less than or equal to 0 and lambda is positive. Therefore, equation 3 is either lambda equal to 0 or 2 x1 plus x2 minus 10 equal to 0. If lambda equal to 0, 2 and 5 yields x1 value 4.5, x2 is 4, and these values of x1, x2 satisfy the equation 4, and but it not satisfied equation 4. Therefore, the optimum solution cannot be determined with the help of lambda equal to 0. So, omit lambda equal to 0, and lambda is not equal to 0, then 2 x1 plus x2 minus 10 equal to 0, and together 1 and 2 yield the stationary value. We have x1 equal to 3.5, x2 equal to 3, implies h of x is a convex and f of x is also a convex, implies Kuntakar condition is satisfied on the sufficient condition for maximum. Therefore, x naught equal to 3.5 and 3 is a solution, and to give NLPP, so the maximum value of z equal to 10.